Okay, hello, so let us go for differential calculus. And so here we go for the definition of derivative, okay, the notion of derivative. We start from the formula here, which is the fundamental theorem of integral calculus, a formula that we recovered in a concrete case, in a physically relevant case, which is the case of the tidal force. And now we change a bit the notation because the function on which we focus is always small f, okay? Here, the function we focus was the small f to be integrated. Now we focus on what in the previous framework is capital F, the integral function. So what we do now is to change a notation. So from now on, we denote by f, small f, the analogous of what in, this is called fundamental theorem of the integral calculus. In the fundamental theorem of the integral calculus is capital F, okay? So this is just to clarify what happens. Now, what we denote by small f is the analogous not of this small f in the fundamental theorem, but rather of the capital F. I give you the definition, and then we'll have other comments. So let small f from AB to R and x bar, an internal point of the interval AB, such that there is m, real number m, which satisfies the following equality. The increment of f from x bar, so f of x minus f of x bar, is equal to the sum of two terms. One is proportional to the increment of f, mx minus x bar, the increment of x, and the rest is Lie law of x minus x bar for x going to x bar. This is very similar to the formula arising from the fundamental theorem of integral calculus here. Okay, just the notation changes, and a function that for a certain point x bar satisfies an equality like that is called differentiable. At the point x bar. And the number m is called the derivative of the function f at the point x bar, and is denoted by several symbols. So, for instance, f prime of x bar, df of x bar, df dx x bar, sometimes also f dot. This is the notation due to Newton of x bar, but in general this is used in physics when the derivative is to be made with respect to the variable time. Okay. However, this is the notation due to Leibniz, and this is the notation due to Newton. They are the two founding fathers of the differential calculus. And I want to stress here that the notation due to Leibniz appears as a fraction where there is a denominator df, numerator df and a denominator dx, but it is not a fraction. It is just a unique symbol, df over dx. Okay? So we gave in the past video a physical application or a physical interpretation of the derivative. Now we can say that in the tidal phenomenon, the tidal force here is the derivative of the gravitational force. This is why gravitational force goes like the inverse of the square of the distance, while the tidal force goes like the inverse of the cube of the distance, because it is the derivative. And now we give a geometric interpretation, and which is very famous, and you all know this geometric interpretation. And this is the usual picture that you can find in all books in the earth, and so you typically have this graph of a function. In general it is concave, so let us draw a convex function. You don't know what is concavity and what is convexity, but of course you know it. What I drew is a convex function. Here there is x bar, here there is x, and of course here you have the height here is f of x bar, and the height here is f of x. And now try to understand what is this. Consider the line joining these 2 points of the graph, and so you start from here. So what is the equation of this line? Of course, there is an angular coefficient. The angular coefficient is the ratio of the increment of the y variable divided by the increment of the x value. And so you have that this is equal to increment of the y value f of x minus f of x bar divided by x minus x bar. Now the game is the following. Let x approach x bar. If x approaches x bar, then you find that this line here, I do it, you have that this line becomes more and more adherent to this point of the graph, x f of x bar. So what we find at the end, so the line joining the 2 points x bar f of x bar, x f of x, approaches or tends to the tangent at an intuitive geometrical level, okay? Of the graph at the point x bar f of x bar. This is what happens. It goes toward the tangent. Now, the angular coefficient of the tangent is this guy here. Limit for x going to x bar of the angular coefficient of the other lines, f of x minus f of x bar, divided by x minus x bar. Now, if f is differentiable at x bar, then you have that f of x minus f of x bar is equal to m x minus x bar plus little o of x minus x bar when x goes to x bar. If we divide by x minus x bar, we find f of x minus f of x bar divided by x minus x bar is equal to m plus little o 1 for x going to x bar. And this means, exactly this means is equivalent, here and here, these all are equivalents. This is equivalent to saying that the limit for x going to x bar of the f of x minus f of x bar divided by x minus x bar is equal to m. And this is exactly the limit that we found in order to deduce, to compute the angular coefficient of the tangent line. So, this in geometrical interpretation is the following: the derivative of f at the point x bar is the angular coefficient of the tangent line to the graph of f at the point x bar f of x bar. This is what we constructed here. But of course, this is very heuristic because in reality, we did never define the tangent. Of course, you can use some so-called differential geometry in order to do that, but you don't know anything about the differential geometry. So, to be rigorous, actually, we did not give any independent definition of tangent. So we cannot say this is the tangent because we don't know what is a tangent. So an independent definition of a tangent line tangent to the graph of a function of at a given point So that for us, differential calculus provides such a definition. Provides a definition for such a tangent. So let me give this definition. The definition says let f from AB to R, which is differentiable at a certain point x bar in AB. Now the line y is equal to m x minus x bar plus f of x bar is said the tangent line at the graph of x, at the graph of f, sorry, at the point x bar, f of x bar, to the graph of f. Okay? Where m is equal, of course, to f prime of x bar, x minus x bar, plus f of x bar. Okay? So the remark, by differentiability of f, so by the definition of differentiability and of derivative, we have the following, that the distance f of x minus y is equal to f of x bar, this is f of x, plus f prime of x bar, x minus x bar, plus lidl of x minus x bar, and this is f of x. And then there is minus y, so minus f prime of x bar, x minus x bar, minus f of x bar. So there are cancellations here and here, and this is y. What remains is just lidl of x on x bar. So, interpretation, the distance, of course for x going to x bar, the distance between the graph of a function and the tangent at x bar, f of x bar, this distance is lidl of x minus x bar as x goes to x bar. So it is an infinitesimal of higher degree, and moreover, the tangent at x bar, f of x bar, and this is very important, is the only, very important, only line whose distance to the graph is Lie law of x minus x bar. Be careful because this is extremely important. Okay? And I want really to clarify this fact. Indeed, let me give some discussion. Indeed, so here, let me repeat quite quickly the graph that we wrote before. Here we have the point x bar, f of x bar, and so let me draw here the tangent. And here another line, which is not the tangent, but passes through the same point. Okay, so this will be y is equal to k x minus x bar plus f of x bar. This is a generic line passing through the point x bar, f of x bar. On the other hand, the black one here is the tangent, so it is y is equal to f prime of x bar times x minus x bar plus f of x bar. Now what I say is that this black line is the only line whose distance from the graph is small in the sense that it is an infinitesimal of higher degree than x minus x bar. So now the distance between the graph of f and a generic line passing through x bar, f of x bar, as, let me compute it, as f of x minus y, which is, so for f of x again we have f of x bar plus f prime of x bar, x minus x bar, plus Lie law of x minus x bar, and this again is f of x. And here we have minus k x minus x bar plus f of x, minus f of x bar. And this is minus y, okay? So the two terms f of x bar cancel each other, and so here we have f prime of x bar, x minus x bar, I get a x minus x bar, so I have f prime of x bar minus k times x minus x bar plus Lie law of x minus x bar as x goes to x bar. Now, the point is that this is equal to the Lie law of x minus x bar if and only if this factor here is equal to 0. Namely, if and only if this term disappears so that Lie law of x bar remains alone. Otherwise, if this guy is different from 0, we have here a term which is not Lie law of x minus x bar, but which is exactly of the same order of x minus x bar. So this is Lie law of x minus x bar if and only if if and only if k, the angular coefficient of the generic line passing through the point x bar f of x bar is equal to f prime of x bar. But if k is equal to f prime of x bar, then the line here is exactly the tangent. So y is f prime x bar, x minus x bar plus f of x bar, or minus f of x bar, I don't remember. Yeah. Is the tangent. So this very simple computation tells us that the tangent is very special from this point of view. It is the only line whose distance from the graph is Lie law of x minus x bar. So in this point, we can say that the tangent is the line that best approaches the graph of f near the point x bar f of x bar. Or, equivalently, the tangent is the best linear approximation to f in a neighborhood of x bar. Why do I insist so much on this point? Because this is a more modern and mature way to look at what is a tangent. Okay, tangent is not only a line that is, oh, it's very nice, it touches the graph only one point. Okay, it is true, and now we also will deepen this geometric point of view. But there is another point. The point is that the tangent can be seen as an approximation of the curve. And if you are bounded to look for linear approximation, this is the best linear approximation. And this opens the way to the Taylor approximation to a function. This is one of the first steps of the Taylor approximation. So start thinking of this problem of approximate complicated functions through simple functions, namely polynomials. If you want, this is a polynomial approximation to a function, and it is a local approximation because we are always in a neighborhood of x bar. So let me stress that this is a local approximation. This point of view will be developed in the month of December, okay? So don't be scared if now you are not able really to grasp everything here. So another point of view, a geometric point of view, a more geometric point of view, is the following. Again, consider the picture that we gave before and go back to this idea of changing the line, changing the line around the point x bar f of x bar. Okay? drawing several lines passing all through this point, x bar, f of x bar. All these lines have two contacts with the curve, but when the second point, x f of x, approaches the first one, x bar f of x bar, these two contact points tend to coincide. And at the end, in principle, when you get the tangent, but it is just an intuition, it can be made rigorous, but it is not in our scope. This is in the scope of a course of differential geometry. Probably you will never meet a course of differential geometry, so this is the only intuition I want to convey to you. So in principle, what happens is that the tangent has a double contact with the graph at the point x bar f of x bar. Okay, this double contact. And this is why, at an intuitive level, again, always at an intuitive level, this is why the tangent is closer to the graph than other lines. Mm-hmm. Okay. It is not completely true that there is only one contact point. There are two contact points again, but they coincide. And so the last thing I want to tell you in this part of the lecture, in the video, is the following remark. Say that the graph of f admits a tangent line at the point x bar f of x bar if and only if f is differentiable at x bar and in all this case y is equal to f prime of x bar times x minus x bar plus f of x bar is the tangent line as at the desired point. Okay, and this is the end for this part. Let's go for the next video where I will compute